Okay, so previously twalipanga function itwala input validation. Okay, we did ourselves a tour in which we created the function twala for input validation. Now, just to remind ourselves, or before we even do anything, let me just create a copy of this so that that donor will F into, and then we don't even know where to get back to. Okay, so I'm going to copy this and paste it. I'm going to rename this as function, maybe function 3. I don't really have a function 3, so we're going to call this as function 3. Because we'll know that the function 3 is just a backup for input validation. Okay, so we're going to say input validation backup. Okay, then we're going to save this, and then because it hasn't been called in OB1, okay, function 3 is not part of OB1, so what are you? Function 3 backup input validation. Maybe let's get rid of this. I'm sure function 3 was what? Function 3 was sample logic previously, so let's just delete this because we don't need for function 3 to be processed. Okay, so now we have function 3 as a backup function in case to our own function 1, the original input validation, we have somewhere to go back to. So having done this, let's see, can we go online? Okay, so the way this function worked, to learn that IAMA protection functions yonse, we're going to wire them externally through normally close contacts, meaning guys is a PLC, the addresses assigned to them will have a true state. Okay, so which is what all this thing was for. Okay, these, I'm sure, network 1 and network 2 were just examples on how these functions worked. Okay, for instance, Moody network 1 to learn that assume memory bit 1.0 is addressed to thermal overload unit wired through a normally close contact. Think of memory bit M1.1, meaning this one, as a check bit, M1.2 as a reset wired through normally close contact. Okay, previously to learn that the reset was going to be wired through a normally close contact, but as we saw Kudi factory IO, it's actually wired through a normally open contact for reset. Okay, so how does that change the logic? Okay, now seeing as how we're not going to be needing the example, this was just so we understood how this worked. Okay, in network 2 we are saying assume memory bit 1.0 is addressed to a thermal overload unit wired through a normally close contact. Think of memory bit 1.1 as a check bit. Okay, whatever this was, this is what we're just trying to explain. But seeing as how we are beyond that point, we're beyond redemption, so we're going to delete this because it's just noise. Okay, transfer to memory bit 1002. Okay, so this was used to load in this function. Okay, in network 3. Okay, let me just save this. So essentially how this is going to work, okay, just so we remind ourselves, we need to remember that a word has got 16 bits. We need to be in binary 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. The hexadecimal equivalent is just 4 values of f's, f f f f. Okay, essentially we're saying that the word has got bits are the true, are the 16. Okay, basically that's just the simplest case of it, because ngamalanda a word has got 16 bits. Okay, 16 possible location for you to put bits which are either true or false. If I say true state, I need to put 1 muma positions yons. If I say false, I need to put zeros in all positions. Okay, so in this state, to learn all the bits that are going to be associated with protection on the external devices are going to be wired through a normally close contact. Okay, so for this to work, I need to load a word equal to true state yama bits yons. Why? Because what's going to happen is this value, okay, w#16#fff f is going to be loaded into the memory word 1002, which is this value word here. Okay, so you're some true state. Okay, depending on how your protection signals are being sent to the PLC, you can change the value associated with this input value. Okay, so what's going to happen, we load this value in network 3. Do we need to put them like this, or do I need to change the order of this? This is just reset. Maybe I'm not changing anything. I just prefer maybe this one comes after this. Okay, so we load this value into memory word 1002, which is 1002, and then of course we've got the memory word 1000. Okay, we've got the memory word 1000. Now you may ask, the importance of this is we're going to think of all the bits in memory word 1002 as check bits. Okay, meaning that because we're using a word exclusive OR, okay, if all these bits are associated with memory word 1002 are true, then for us to get an output, all the bits in memory word 1000 will need to be 0, because if it's 1 1 1 1 0 1 0 1, okay, that's how they are going to work. So the only other thing you need to appreciate, okay, is this. Okay, if memory bit 1000.0 has got the same place value as memory bit 1002.0, and then it's got the same position as memory bit 1004.0. okay, and it does have the same place value as memory bit 2000.0. okay, so you see how these will relate. In the bit position of memory bit 1000.0, the result of whatever processing is in between is going to be held in memory bit 2000.0. okay, so this is how they're going to move. So the same holds true that memory bit 1000.1 has got the same place value as 1002.1, and of course memory bit 1004.1, goes without saying, memory bit 2000.1. okay, all the way up to memory bit 1000. If it's a word value, we're talking about 1001.7. okay, we have the same place value as memory bit 1003.7, same place value as memory bit 1005.7, same place value as memory bit 2001.7. okay, like so. So this will be the in between. These will be the extreme addresses for all these bits. The memory word 1000 is going to run from memory bit 1000.0 all the way to memory bit 1001.7. okay, and so with the other memory bit positions. okay, that memory word 1002 will run from memory bit 1002.0 all the way to memory bit 1003.7. Okay, so this is how they're going to relate in this order. Now, why I'm telling you this, because now we need to do some adjustments. Okay, but first we noticed that previously when we were looking at factory IO, that the reset was actually wired through a normally closed contact. So what we're going to do is we're going to do system reset. Okay, system fault reset, which is this one here. Okay, and then what else do we need to do? This one was just meant to show us the behavior of these bits. Okay, we're just meant to see the behavior of the bits, or maybe we can run through it. Okay, we can run through this. Okay, so to help us with this, maybe let's just do this. Which one do we use? 1000 and 2000. Okay, let's see what we were getting. Then this one I'm going to say modify. Okay, maybe I really don't want to modify this. What I do want is I need to use a normally closed contact, and then I need to delete it, or rather cut, paste there, delete this, and then of course download. Okay, then monitor, then 1004, 1008. These were just example networks, but now that we're here, we want to prove a point, so we can get rid of these, but instead maybe insert a network right about there. And then of course we're saying, what are we saying? We're saying, okay, maybe we're going to do this. I hope this is the right thing we're doing. So exclusive OR. So exclusive OR would be what? To be if this is 1 1 1 0. So meaning I would need to negate this. A bit logic, I need to negate this. Okay, so that I get the exclusive OR result. Okay, so what I'm just saying is 1 1 true, false, but because this is normally closed, this is going to be true, negate, output 0. Okay, so we're going to get an output coil. Okay, so let's see, memory bit 1000.0, then memory bit 1002.0, and then what else do we need? We need to reset, and then by way of reset, we essentially talking about the reset bit. Okay, this has been moved to memory bit memory word 1008 point, okay, which are just all ones. Okay, so the same memory word 1008 point is having two values. Okay, so in this case we're saying if it's not pressed, we need to move this value into memory word. Okay, and then to reset, move this value into this one. Okay, so which puts this one. Okay, in this case, if since as how we're moving ones into this location, I'm thinking this needs to be open. Okay, this needs to be open, and then memory bit 1008.0 will be associated with okay, let's say memory 2001.0. okay, so we pick something which is out of range of this. No, not 2001, maybe 2002. So this is just purely for illustrative purposes. So get this, so paste there, and then we have something like this. Okay, so memory bit 1002.0 already has the bit. Okay, so clearly because we're moving ones in this position, I'm thinking the right configuration will be this needs to be open. Okay, this needs to be open so that we get the right representation. Okay, so the behavior will be like this. Okay, so when this bit is true, modify to 1, we can reset, okay, by way of modify to 1, modify to 0. Okay, we have something like the system is reset. Okay, but if this bit became false at any one time, so modify to 0, then you'd have this address becoming true. Okay, and then this would actually represent a faulted state, or it would monitor the behavior of this system. Okay, now the reason why I'm even showing you this is because sometimes, because of maybe a loose wire, you lose the connection to the PLC, and if it's a protection input, that will be flagged as a fault. Okay, so there'll be a situation whereby at some point you get this loose connection, the wire becomes loose, the system trips on account of a fault, and then you chime in a machine mwasasangati you check that it's actually the system is okay. You tripped out on account of a fault which was basically just due to a loose wire, and then the system stops, the wire gets into position, and you are not able to pinpoint the exact fault location, which is why we're saying those transitions in the protection inputs should not self-reset. Okay, you should be able to reset the push button. Okay, but you need to also reset the PLC. Okay, which is why this thing here comes into play. Okay, so now that this is taken care of, we're going to delete this, and then let's save this. So the only other thing now we need to do is to ask a very simple question: how do we align what we have here to the mapping? Okay, how do we align the two? So what we're going to do is really rather simple. Okay, what I'm going to do is the following. I'm going to open the mapping, input output mapping, and again I'm going to make a copy of this. Okay, because this is just so we appreciate what we're trying to achieve. So function 4 is the backup. Okay, so I'm going to open function 2 so that we see what this is all about. Okay, so let's see protection. we said all the addresses with memory bit 20.0 were assigned to be protection inputs. So maybe I'm going to do the following. I'm going to cut this. I'm going to cut this. Okay, I'm going to cut this. And then I'm going to say insert network. I'm going to paste there. And then I'm going to save this. I'm not changing anything. I'm just trying to create a network for protection inputs. Okay, for protection inputs. Okay, I'm just going to create a section, a network for protection inputs. And the reason why this is necessary is because of what's about to come next. Okay, so clearly what we're using in creating our program, all the logic inside the functions and functional blocks, us, we're just going to be using the memory bit addresses. Okay, we are not interested in the actual physical inputs and outputs, but we're using the memory bit addresses for all those inputs in our logic. Okay, so what I'm going to do is the following. Okay, what I'm going to do is the following. On this part, okay, I'm going to make use. Okay, how many protection inputs do we have? We have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 13 or so. Okay, and a word is like 16 bits, so we have more than enough. So what I'm going to do is the following. Okay, I'm going to do the following. Okay, this one, I'm going to pass the state of these physical inputs to bits associated with memory word 1000. Okay, so the first one will be like memory bit 1000, 1000.0. okay, like so. Memory what? Memory bit 1000.0, and then essentially that's going to represent the station 1 emergency stop. Okay, and then memory bit 1000.1 is going to be for the emergency stop in the second station. The memory bit 1000.2. okay, then we're going to have memory bit 1000.3, and then we're going to have memory bit 1000.4. Then we're going to have memory bit 1000.5, memory bit 1000.6. We're not going to assign the flow because the flow is essentially conditional. Okay, it would only create problems for everyone else. Okay, because the flow is the result of the lubrication pump being switched on. So I think the flow is an exception to what we're trying to do. Okay, and then main contactor 01, I think this is the auxiliary contact. Let's see, what is this now? Let's see, MC01. What are you about? So all filter bypass McDowell. Okay, so this is a protection input. So this we're going to assign to memory bit 1000.7. Okay, and then this other one will be memory bit 1001.0. okay, then we have memory bit 1001.1, then memory bit 1001.2. okay, so we'd have something like this. Okay, essentially the only thing I'm doing is I'm passing the signal state of the peripheral input, okay, meaning the signal states of the emergency push buttons, the thermal overloads, and everything else in between. I'm passing them on to the bits in this memory word 1000. This is just the first part. Now we need, like we've just highlighted, okay, what we're using are the bit positions, or the memory bit addresses in our logic. So these bits, okay, because on the output side of things, okay, on the output side of things we have memory word 2000. okay, so how do these stack up now? Okay, these will stack up in the following order. Okay, we're saying, okay, because these are actually like so what we're saying is, just so we don't really get it messed up, we can just here we can do the following. Okay, we need to pass we know that this memory bit 1000.0 will be part of the processing in this function, or in this network. Okay, so these bits will be applied on the input side. Okay, but what we're interested in is the output side, this section here. These bits in this memory word 2000 are the ones now which are going to be mapped to the bits that we're using in our logic. Okay, so what we'll just say now is AND memory bit 2000.0. why do I keep writing 200? Okay, 0.0 is going to be passed to this address. Okay, it's going to be passed to, oh, okay, maybe do I need to copy everything, including the italics? Okay, the brackets there. Okay, so this now maps the output. Okay, so the same thing, we can do this without thinking now. Okay, we can just do this without thinking about it, because now we need to come here. So, and memory bit 2000.1 will be assigned to this one here. Okay, and then of course we need to copy this and say memory bit, okay, and memory bit 2000.2 will be assigned to this address. Okay, and then we need to copy this. Okay, and say and memory bit 2000.3 will be assigned to that. And then we'll can copy this one here and memory bit 2000.4 will be assigned to this address, and then we're going to copy this, and then we're going to say and memory bit 2000.5 is going to be assigned to this one here, and then and memory bit 2000.6 is going to be assigned to this one here, okay. We don't have anything here. Okay, seeing as how these are not really maps to anything, I may just want to have them maybe at the end, because maybe we can move this. Oh, I know it. They were part of the original. Nah, I'll just leave them here. And memory bit 2000.6 is passed on to this, and then and memory bit 2000.7 is passed on to this, okay. Then I need this address, and then memory bit 2001.0, okay, is passed on to that address, okay. And then this one here, we're saying and memory bit 2001 point what? Point 1, memory bit 2000.1, memory bit 2001.0, memory bit 2001.1 is passed on to this, okay. And then eventually, conclusively, we'll say memory bit, okay, and memory bit 2001.2 is maps to 2AE1, okay. So now this is what we have, okay. But then you're like, oh, what is that we're doing? Essentially, what we're just doing is we're trying to have a level of control over the transition of the protection inputs, okay. If the protection input transitions from true to false, we need to be aware of that transition, meaning we need to reset the PLC. And we don't really want to be creating separate networks for reset, okay. All that reset business is handled by what's happening in network 2, okay. That's what's happening in this system, okay. So how do we prove what we have done? So the only thing is we can just save this. So basically this is what we wanted to do. This sets that puts us in a position to simulate. So the moment of truth. So the moment of truth. How do we prove what we're saying is the right thing? So let's look at what we have here. Okay, right about now. So as in right now, we need to just come to where it says protection inputs, okay. So protection inputs, we're saying, what are we saying with the protection inputs? Okay, So what you see from here is that the status of the protection input is actually true. Okay, but why are you not reflecting the friends? Emergency stop. So memory bit 1000, 2000. Okay, and then station 2, the status of this is false. So false. So we expect the true state in the (110). Okay, so essentially what it means is if the emergency push button from the peripheral input is false, it means the emergency push button has been actuated, which explains why the peripheral input is false in all accounts, but the emergency stop within the program is designated as being true. Okay, so false, true. Okay, false, true. Okay, false, true. So for all the states of the protection inputs, that's what we are seeing. Okay, let's see. Okay, so it seems to be right. So now the number of bit boolean inputs, okay, I don't know. Okay, we can put 16. Number is 16. Boolean outputs, maybe we can put 8, because we really don't have a lot of boolean outputs. Okay, so this is what we have. Reset, we're saying is 1.7, right about there. So I1.7 is system reset. Okay, so we're talking about a reset situation. Okay, talking about a reset situation as in this position. Okay, so let's zoom in. Let's do this. Okay, so we're able to do a reset. Okay, if we come to protection, we're going to need the station emergency push buttons. Push buttons, these are emergency push buttons, so we're going to just copy. We're just going to copy this. Okay, so we've got how many of these? 1, 2. We've got 1, 2, 3, 4. Is it 1, 2, 3, 4? Okay, so we've got 4 emergency push buttons. So this is one. We're going to create okay, so that we have 4 emergency push buttons. Okay, and then the way do I need this? Okay, maybe let's do it like this, and then may want to have these actuators. So the first one is station 1 emergency stop. Okay, so this is going to be come on, station 001 emergency. Okay, so it takes care of this. Then we've got station 2, station 3, then station 4. Okay, so we want to copy this. This is going to be station 2. And then this is going to be station 3. and then this is going to be station 4. Okay, this is going to be station 4, like so. So we have all the emergency push buttons. Okay, station 1 emergency stop, station 2 emergency stop, station 3 emergency stop, station 4 emergency stop. Then the other thing that we need is what? We need the 4DE2, and then we need 4DE3. Okay, so we need 4DE2, we need 4DE2, we need 4DE3, and then we need T0102. Okay, is this pin what? T0102 is lubrication oil temperature. Okay, lubrication oil temperature, then the flow wasn't part of that, the loop oil filter blocked, the thermistor, then this should be overcurrent for the main drive. Okay, so emergency stop, so we need 4DE2, then we need 4DE3. Okay, so what do? We want to copy this. So this is 4DE2. Okay, so this is 4DE2. We want to copy this. Oh, come on. This is going to be 4DE3. So we've done 4DE2, we've done 4DE3, and then T0102. Okay, so we're just going to copy this. Then this is going to be T0102. Okay, which is just the T0102 is in that position. The comment is that this is just the loop oil temperature. Okay, T0102, and then the McDowell flow switch, loop oil filter blocked, MC01. So this is MC0101. Okay, I can copy anything. Let me go offline. So this is going to be MC01. Okay, this is going to be T0102. So now we need to copy this. This is going to be MC01 01, which is this one here. Okay, this is just the loop oil filter blocked. Okay, which is because the comment is this one, loop oil filter bypass switch. So this loop oil filter bypass switch is MC0101, and then the main drive thermistor relay. Okay, so this is going to be TR02. So I'm just going to copy this, and then I didn't copy the MC0101. I need to copy this, and then this is going to be TR02. Okay, and then the other one should be the main drive overcurrent protection, which is H5A. Okay, H5A. I'm going to copy this. And then of course this is going to be H5A, and then the next one is going to be H5A. We're going to have 2AE1. Okay, Then we're going to have 2AE1. Okay, we're going to have 2AE1, and then this is done, and done. Maybe I don't need this. I can just close them all so that we get a better view of what we're doing. Okay, so first off, we've got the reset, which we have confirmed, and then we've got the 4 emergency stop push buttons by way of okay, let me get rid of this also, by way of station 001 EMR, which is this address, station 002, okay, then station 003 and station 004. Okay, so 01, 02, 03 and 04. Okay, and then right after that we should have 4DE2. After the stations we have 4DE2, 4DE3, so we have 4DE2, we have 4DE2, 4DE3, 4DE2, 4DE3, we have T0102, T0102, and then we have MC01, 01, and then MC01, 01, then we have TR02, TR02 is on the far end, it's this one here, okay, TR02, and then after that we have H5A, and then we have 2AE1. Okay, now we're using the emergency push button because it's essentially every other protection input is going to behave as though it was an automated emergency push button, and because the emergency push button in factory IO is wired through a normally closed contact, so which is why, because if we're assuming that Yonsama signals are kuri PLC, if they are related to the emergency function, they are wired through the normally closed contact of those physical devices, which is how this is still valid. We just need to do one other thing. We need to assign these addresses now. Okay, so you notice that where the protection functions are concerned, that the first station emergency push button is assigned to memory address 5.0. okay, so we may want to do some edits. Okay, so configuration, so what's the maximum? So 16 by 5. I don't know, I don't know what the limit is for this. Hopefully, how many inputs does it allow me? Okay, so if I say 80, okay, I don't need to go that far. So let's see, if I say I need to 8 by, okay, let's say if I need 50 inputs, is 5 going to be within range of this? So 50, I only need to go as far as, anyway. So if I say 48 inputs, okay, so if I say 48, inputs, I'll go as high as 6.7, which is fine. So now that we have this sorted out, you notice that the first emergency push button is assigned to input address 5.0. so station 1 goes to 5.0. okay, so station 1 goes to 5.0 like that, and then I think these are just in sequence. So station 1, station 2, station 3, station 4. okay, station 4 is assigned to 5.3, and then after that we're talking about 4DE2, which is assigned to 5.4. so is it 4DE2? 4DE2 is assigned to 5.4. then 4DE3 is assigned to input address 5.5. So 4DE3 is assigned to 5.5, and then T01 is assigned to address 5.6. Okay, so T01 is assigned to 5.6, and then the flow switches we did not map. The filter blocked is assigned to 6.1. Okay, before that, yes, it's assigned to 6.1. So MC01 is assigned to 6.1, I think. Is assigned to 6.1. Is assigned to 6.1, input 6.1, and TR02 is assigned to 6.2. Okay, TR02 is assigned to 6.2, and then H5A is assigned to 6.3. Okay, so H5A is assigned to 6.3. So H5A is assigned to 6.3, and then 2AE1 is assigned to 6.4. So 2AE1 is assigned to 6.4, and I think that's the end of that. Okay, reset is done, so I may need to save this, and then of course we're going to have to look at this for protection. Okay, because this is under protection inputs. So now we see that we have a true state for all the protection inputs. Okay, so we have a true state. So these are the peripheral inputs. They are actually true. Okay, these are true. If you check on the state of this, on the status, so the emergency push button for the first station is true, and the true state is being passed on to the corresponding bit. So if we get into factory IO and we actuate the first station emergency push button, you look at this bit here. Okay, it becomes false. Okay, and then if it becomes false, the only other thing is, if it's true, do a reset. Okay, you notice that the emergency push button status as viewed in the program is actually false. Okay, it's actually false. Okay, but when we do actuate this, okay, becomes true, and then this one becomes true. But when this is reset, okay, for this station, okay, for this station, we do a reset. Okay, okay, it's false. We do a reset. It's monitored as a fault in this position. Okay, so if we reset, it's still monitored as a fault. Okay, so we need to do a reset, and then we know that the system is healthy. Okay, the same thing goes for the second position, this position here. If we actuate, it's monitored as a fault. If we normalize, it's still monitored as a fault. If we reset, the system clears. Okay, so in this way we can basically monitor the state of any signal that is fed to the PLC. If it's important to be monitored, then we can monitor it in this way without having to individually create logic for each and every input that we need to monitor. We can just come here and look at the address assignments, which addresses are free. Okay, so lastly, if we're talking about 2AE1, 2AE1 is the last man standing in this network. Okay, so 2AE1 is here. Right now it's okay. So if we actuate this, the fault, okay, emergency stop, normalize, still monitored as a fault, do a reset, clears. Okay, so basically we know how we can monitor all the system input variables. So tukakonkanyapo kufuma apa so that number tukambe kushita create number logic for this, because number two alanga over to ngachita assign ama inputs nama outputs over to ngachita assign. Aye. Okay, kale bari kamkwai.